So in today's lecture, we'll be looking at ionization energy as a topic, and the lesson objectives before us are: 1. Students should be able to define and use the term ionization energy, then identify and explain the variation in successive ionization energies of an element, then construct equations to represent first, second, and subsequent ionization energies, otherwise known as successive ionization energies. Understand that ionization energies are due to the attraction between the nucleus and the outer electrons. Explain the factors influencing the ionization energies of elements in terms of nuclear charge, atomic or ionic radius, shading by inner shells and subshells, and spin pair repulsion. So please, I want us to listen attentively and get the best out of today's lecture. So we're starting with ionization energy. What is ionization energy? Ionization energy simply means the amount of energy that is required to completely remove an electron from a gaseous atom. The amount of energy that is required to completely remove an electron from a gaseous atom. It can also be defined as the amount of energy required to remove an electron from an isolated atom or molecule. Now, to remove an electron from an atom, energy is needed. So you can see that ionization energy is an endothermic process. That means the enthalpy change is positive because energy is needed to remove an electron. This is because of the electrostatic force of attraction between the positive nuclei and the electrons. The nucleus contains the proton, which is positively charged, so it has an attraction for the electrons. So energy is needed to remove the electron. So the amount of energy required to completely remove an electron from a gaseous atom as a result of the attraction from the nucleus is what we call ionization energy. Simply put, as the amount of energy required to completely remove an electron from a gaseous atom. So we have what we call successive ionization energies. Successive ionization energies are defined such that one electron is removed at a time. You are removing one electron at a time. So, since you are removing one electron at a time, and there's an attraction between the nucleus and the electrons, successive ionization energies for an element will always increase. Because as you are removing an electron one at a time, what happens? The positive nuclear charge increases. So this is because the negative electron has to be removed from an increasingly positive ion. So removing one electron makes a plus one ion. So we'll call this the first ionization energy. So which is the energy required to remove 1 mole of electron from 1 mole of a gaseous atom to form 1 mole of a gaseous plus 1 ion. We call it first ionization energy. I repeat again, the amount of energy required to remove 1 mole of electron from 1 mole of a gaseous atom to form 1 mole of a gaseous plus 1 ions. So this is an equation. You can see the equation representing the first ionization energy. The energy required to remove 1 mole of electron from 1 mole of a gaseous atom to form 1 mole of a gaseous plus 1 ion. So we'll call it successive ionization energy, which is first ionization energy. First, for example, if we take sodium, for example, the first energy of sodium, gaseous atom, to form a gaseous plus 1 ion. So you remove 1 electron at a time. So they are defined such that 1 electron is removed at a time. So we call it first ionization energy, which is the energy required to remove 1 mole of electron from 1 mole of a gaseous atom to form 1 mole of a gaseous plus 1 ion. Just the way we have second ionization energy, third ionization energy, fourth ionization energy, depends on the number of protons. So that's what we call successive ionization energy, which is a continuous process. We have the second ionization energy. So if the second electron is removed from each ion in a mole of gaseous plus 1 ions, we call it the second ionization energy. So second ionization energy is the energy required to remove 1 mole of electron from 1 mole of a gaseous plus 1 ion to form 1 mole of a gaseous plus 2 ion. You can see the equation we have here. The energy required to remove 1 mole of electron from 1 mole of a gaseous plus 1 ion Energy required to remove 1 mole of electron from 1 mole of a gaseous plus 1 ion to form 1 mole of a gaseous plus 2 ion. We call it second ionization energy, from a gaseous plus 1 to form a gaseous plus 2 ion. Then removal of a third electron from each ion in a molecule of gaseous plus 2 ion is called the third ionization energy, which is the energy required to remove 1 mole of electron from 1 mole of a gaseous plus 2 ion to form 1 mole of a gaseous plus 3 ions. So ionization energies are measured under standard conditions. That's why the units are kilojoule per mole. So we'll call it successive ionization energy. First ionization energy, second ionization energy, third ionization energy, fourth ionization energy. So if I were to write fourth ionization energy, it is the energy required to remove 1 mole of electron from 1 mole of a gaseous plus 3 ion to form 1 mole of a gaseous plus 4 ion. That is energy required to remove 1 mole of electron from 1 mole of a gaseous plus 3 ion to form 1 mole of a gaseous plus 4 ion, form 1 mole of a gaseous plus 2 ions. We call it the fourth ionization energy. So successive ionization energies for an element always increase. And this is because the negative electron has to be removed from an increasingly positive ion. So that is what we mean by what successive what ionization energy. Please, I want us to know that the unit of ionization energy is in kilojoule per mole. So we'll talk about successive ionization energy. You are removing 1 electron at a time. So to interpret successive ionization energies, what happens is that we can use the arrangement of electrons in an atom to interpret the successive ionization energies. Now, the arrangement of electrons in an atom of sodium can be deduced from the values of successive ionization energies. Now, if you look at the electrons, you know, some of the electrons are very close to the nucleus, while others are farther away from the nucleus. So this is the first electron. So the energy required to remove this, that's what we call what? The first ionization energy. The electron required to remove the first electron. Very easy to remove. Very easily what? Remove. Because it is farther away from what? From the nucleus, from the positive nuclear charge. It is farther away from the attraction of what? Attraction of the nucleus. Then you have the second set of electrons. 8 electrons, less easily what? Removed. Then the innermost electron, which is the 10th and the 11th electron, the 2 electrons are very difficult to remove. So this is the first electron. Remove this, you have the first ionization energy. Removing this, you have the second ionization energy, third ionization energy, fourth ionization energy, fifth ionization energy, sixth ionization energy, seventh ionization energies, eighth ionization energy, ninth ionization energy, the 10th ionization energy, and the 11th ionization energy. You are removing 1 electron at a time. As you remove the electron, you get closer to the nucleus, so the ionization energy will increases as a result of what? The attraction from what? From the nucleus. So it's easy to interpret what? Successive ionization energy from the arrangement of electrons in an atom. So the farther the electron is from the nucleus, the lower the ionization energy. The closer the electron is to the nucleus, the higher the ionization energy, which is as a result of what? Attraction from the nucleus. So looking at interpreting successive ionization energies, so we can use a graph of successive ionization energies against the number of electrons to interpret what successive ionization energies. So this is a graph of successive ionization energies against the number of electrons removed for sodium. Now if you look at the graph, which is a graph of the ionization energy against the number of electrons, this is sodium. Sodium is 11. Sodium have atomic number of 11. The atomic number of sodium is 11. And the atomic number is the number of protons. The number of protons is equal to the number of what? Electrons. So this is the outermost electron, which gives the first ionization energy. It has the lowest ionization energy because of its distance from what? From the nucleus. So there's less attraction from what? From the nucleus. So this is the outermost electron with the lowest ionization what? Energy. So this is the second electron, third, fourth, fifth, sixth, seventh, eighth, and what? ninth, you discover that the difference between the ionization energies, the energy of the second, third, fourth, fifth, sixth, seventh, eighth to ninth is very small. It's not that what? It's not that large. Then this is the 10th ionization energy and the 11th ionization energies, which are the electrons that are closer to the nucleus, and there's a greater attraction for the electrons, as a result of what, the increased positive nuclear charge. So they are closest to the nucleus and they have the greatest ionization energy. So we can use this to interpret what successive ionization energy, that the distance of the electron from the nucleus affect what the ionization energy. Those electrons that are far away from the nucleus have less ionization energy, are easily removed. Then those ones that are closer to the nucleus, they have the highest ionization energy and are very difficult to be removed. So you can use a graph of ionization energy against the number of electrons to explain or to interpret successive ionization energies. So I want to look at the uses of successive ionization energies. So what do we use successive ionization energies for? One of them is that we can use it to predict or confirm the simple electronic configuration of elements. Yes, we can use successive ionization energies to predict or to confirm the electronic configuration of elements. We can also use it to confirm the number of electrons in the outer shell of an element. Yes, once we know the number of electrons in the outer shell of an element, then we can predict the group to which the element belongs. So another use of successive ionization energies is to confirm the number of electrons in the outer shell of an element and hence the group to which the element belongs. That is the group number of a particular element. And now I want us to know that the jump between successive ionization energies is particularly large after a noble gas configuration is reached. So when you get to a noble gas configuration, there's a big jump. The jump between successive ionization energy is large after a noble gas configuration is reached. So please, I want you to take note of that. So this is a typical examination question to confirm the use of successive ionization energies. Now, the successive ionization energies of an element X are shown in the table below. So this is a question. Let's see how we're going to answer this question. You are now asked which group in the periodic table does X belong to. So you can see that we're given the table of the successive ionization energies from the first to the 10th ionization energy. So which group in the periodic table does X belong to? So the first thing you do is that you look at the ionization energies where we have a big jump, where there's a large difference between the ionization energy. So where there's a big jump, that is where you look at, then you can determine the group to which element X belong in the periodic table. Now what we have to do is that we look for a large jump in the value of the ionization energy. And if you look at the values, you discover that it occurs between the 6th and the 7th ionization energy. That is where we have the biggest jump. Look at it between the 6th and between the 6th and the 7th ionization energy. The 6th ionization energy is about 8,500, and the 7th ionization energy is about 27,100. So there's a large difference. There's a big jump. So the 6 electrons have been removed comparatively easily. So the removal of the 7th electrons require about 3 times the energy required to remove the 6 electrons. If you look at the difference, so there must be 6 electrons in the outer shell of X. So element X must be in group 16 of the periodic table. That means it belongs to group 6, which is group 16, also known as group 16 of the periodic table. So with this, you can use successive ionization energy to predict the group number of an element. All you have to do is to look at the ionization energies and try to spot where you have a big jump between the ionization energies. So it's as simple as A, B, C. So please, I just want us to solve as many questions as possible as we, after the lecture, and you can see that it's very, very easy. So this is a typical examination question for us to attempt based on what we've done. We are given the first 6 ionization energies of an element as follows. You are now asked which group in the periodic table does this element belong to. So explain your decision. So all you have to do is just to look for the ionization energies where we have a big jump, the points where we have what a big jump between one ionization energy and the next what ionization what energy. Then you can tell the group to which the element will belong. Then the next one is draw a sketch graph to show the log values of the first successive ionization energies of a group 2 element. So you can just pick a group 2 element. It can be calcium, it can be magnesium. Just pick a group 2 element, then you plot a graph of the ionization, successive ionization energies against what the number of electrons. So please, I want us to attempt this. It's as simple as ABC. Please, if you encounter any difficulty, feel free to reach out to me. I'm Mr. Joseph, your chemistry teacher. I'm always there for you. Please feel free to reach out to me. You can reach out to me on the comment section. Just go to the comment section, or you reach out to me in any form. I'm always there for you, and I'll be there for you. So please, I want you to attempt this, and you find it that it's very, very easy. So let's look at the factors affecting ionization energies. What are the factors affecting what ionization energies? The first one we want to consider today is the size of the nuclear charge, the positive nuclear charge. You know, the atomic number is the number of proton. So a proton is positively what charged. So that means that as the atomic number increases, the number of protons increases. The positive nuclear charge also what increases. So as the positive nuclear charge increases, you know, the ionization energy is bound to what increase, because the bigger the positive charge, the greater the attractive forces between what the nucleus and the electrons. So more energy is needed to overcome these attractive forces if an electron is to be removed. So in general, ionization energy increases as the proton number what increases, because as the proton number increases, the positive nuclear charge will increase. So the size of the nuclear charge affects what the ionization what energy. So it's very, very important as we proceed. So please, I want you to take that into consideration, that the size of the nuclear charge can affect what the ionization energies. That as the ionization energy increases, that the ionization energy increases as the proton number increases. Because the proton number increases, the positive nuclear charge increases. So the bigger the positive charge, the greater the attractive force between the nucleus and the electrons. So ionization energy will definitely increase. So the next one is the distance of outer electrons from the nucleus. The distance of the outer electrons from the nucleus. You know, electrons that are farther away from the nucleus can easily be removed compared to electrons that are closer to the nucleus. Now, what happens is that the force of attraction between positive and negative charges decreases rapidly as the distance between them increases. So electrons in shells farther away from the nucleus are less attracted to the nucleus than those closer to the nucleus. So the further the outer electron shell is from the nucleus, the lower the ionization energy. The closer the electron is to the nucleus, the higher the ionization energy. So distance of the electron from the nucleus is a major factor that affects the value of the ionization energy. So electrons that are farther away from the nucleus can easily be removed compared to those electrons that are closer to the nucleus as a result of attraction from the nucleus. You know, the force of attraction between positive and negative charges decreases rapidly as the distance between the electrons and the nucleus increases. So the next one is shielding effect of inner electrons. That's what called shielding effect of the inner electrons. Shielding. You know, the inner electron, they shield the outer electron from the effect of the nuclear charge. From the effect of the nuclear charge, because there's a greater attraction from the nucleus. As all electrons are negatively charged, they repel each other. Electrons in the inner shells repel electrons in outer shells. Full inner shells of electrons prevent the full nuclear charge from being fed by the outer electrons. This is called shielding. So the greater the shielding of outer electrons by the inner electron shells, the lower the attractive forces between the nucleus and the outer electrons. The ionization energy is lower as the number of full electron shells between the outer electrons and the nucleus increases. So the shielding effect of inner electrons affects what? Ionization energy is a major factor that affects what? Ionization energy. So shielding effect, that the inner electron, they shield the outer electron from the effect of the positive nuclear charge. So the ionization energy is lower as the number of full electron shares between the outer electrons and the nucleus what increases. So the greater the shielding, the lower the ionization energy. The less the shielding, the higher the what? Ionization energy. So it's as simple as A, B, C. The next factor is what's called spin pair repulsion. Spin pair repulsion. From our previous studies, we discovered that we talk about an orbital, that an orbital is a space or region where one is likely to find an electron, and an orbital can take a maximum number of 2 electrons that spin in opposite direction based on Pauli exclusion principle. Now, what happens is that in an orbital takes a maximum number of 2 electrons and they spin in opposite direction. In an orbital, there are electrons, so the electron they spin in opposite direction. So this orbital contains what? A pair of what? Electrons that spin in opposite direction, and this orbital contains what? An unpaired electron. This is an electron negatively charged. This is an electron that is negatively charged, negatively charged. So like charges repel each other. So in an orbital, the electrons have repelled themselves already. So it is easier to remove an electron from a paired orbital compared to what? An unpaired orbital. So spin pair repulsion is a factor that affects ionization energy. That electrons in the same atomic orbital in a subshell repel each other more than electrons in different atomic orbitals. This increased repulsion makes it easier to remove an electron. So force ionization energy is decreased. So in a paired orbital like this, it is easier to remove an electron from a paired orbital where the electrons have repelled each other as a result of spin pair repulsion compared to what? An orbital, which is what? Unpaired. So it is difficult to remove an electron from an unpaired orbital compared to what? A paired orbital, because in a paired orbital, spin pair repulsion has taken place, the electrons have repelled themselves what? Already. So spin pair repulsion is one of the factors that affect what? Ionization energy. So I'm Mr. Joe, your chemistry teacher. Subscribe to my YouTube channel, like, share, and comment. Thank you for listening. I'm Mr. Joe, once more, your chemistry teacher. Please subscribe to my YouTube channel. Mr. Joe, your chemistry teacher.